Hello Internet, my name is Quinn and this is Blondihacks. Well, with the Pennsylvania A3 switcher boiler completed, I thought this would be a good time to do a little Q&A. It's been a long time since I've done a project that has generated quite this many questions and comments, some politely phrased, some less so. I think that speaks to both people's interest in the project and also the fact that this is a very niche hobby that is not well understood, I think, outside of that hobby. And I've brought a lot of kind of mainstream eyes on it. So there's a lot of techniques and things that are old hat in model engineering that maybe are new to you, and so you may not understand why things are done the way they are, or some of the broader aspects of all of this work. So hopefully I can get some of those questions answered here. Many of these questions are ones that I've frankly answered in many videos before, but people don't watch every video. Hopefully at least a few of you will watch this one. As you know, I don't tend to answer comments in YouTube comments just because A, there's too many of you, and B, people tend to ask the same questions over and over. Again, even if I answer them in many, many videos, people keep asking them. So I also have an FAQ on my website that I link to in the description of every video. So if you do have a question about general machining stuff that you see in my channel, maybe go check out that FAQ. And for the boiler related questions and building the locomotive in general, hopefully this video will help. Let me start with an overall kind of general statement about the idea of intellectual humility. Model engineering is a very old hobby. It's 100 years old, and to put a fine point on that, I have here a collection of model engineering articles from 1884. These guys were building steam engines and locomotives with treadle lathes and files. And the point I want to make here is that everything that you see me doing on my channel is bog standard model engineering. It's the way that people have been doing it for over 100 years. And so the stuff that you see me doing is not things that I've invented or that I'm coming up with or experimenting with. The reason that's important is because if you want to question the things that you see me doing, keep in mind that people have been doing it for a very long time. So there's probably good reasons why things are being done that way. So if you're interested in what those reasons are, feel free to ask, but be careful about assuming that the things that you see are probably being done the wrong way, because again, generations of very smart people came along before both of us and figured all this stuff out. So keep that in mind as I answer some of these questions, that it takes a certain amount of hubris to doubt 100 years of wisdom on these topics. All right, so let's get into it. I'll start with the number one question that gets asked about a dozen times in every single boiler video, no matter how many times I answer it, and that's, why don't you just TIG weld it? Now, that's a very easy thing for you to say, but A, I don't have a TIG welder, but B, TIG welding is not an easy skill to learn. It takes a lot of practice, and you can't just create adequate joints in this case. You have to be able to create gas and pressure tight joints, and on an exotic metal to boot. If you don't know all the details of which filler rods to use and so on copper, you'll end up with brittle joints. The end result won't be safe. And again, TIG welding exotic metals on top of that is a rarefied skill that is pretty difficult to acquire. Silver soldering is pretty easy to learn. Anybody can do it with a little bit of practice, and with a little more practice, you can do it good enough to make a boiler. So that's why we use silver soldering for this. There are people who do TIG weld model boilers. There are some companies in the UK that make them commercially, and you can buy them from them. They're all TIG welded, but to give you a sense of the skill involved in making them, those boilers range in price from $5,000 to $10,000. So that's why most hobbyists opt to simply silver solder our own. Let's talk a bit about boiler inspections. A few people were interested in that. Every jurisdiction, every town, city, county, province, whatever, has different bodies that regulate boilers. Steam boilers are still very much a part of modern life. They're still used in all sorts of situations, and so there are currently active regulatory bodies that certify and inspect boilers. Generally, they all have some sort of lower limit to where you need an inspection. Typically, it's based on size and or pressure. So again, check your local laws, but typically something like 4 inches in diameter, 12 inches long, and something like 100 psi is pretty typical to where a boiler of that size will not require inspection. And so you can run that in your backyard all you want, and no one needs to know about it. If you want to build something larger, you may have to get it inspected. If you're going to run a boiler in public, then other things start to kick in. So whoever is running the event where you're running that boiler in front of the public is going to have insurance, and they're going to have their own rules and so on. So typically for a locomotive boiler, you're going to get the boiler inspected and certified by the club where you're going to be running that locomotive. The club track is going to have their own rules, their own certification process. These vary, again, club to club. Some boiler inspections involve looking at the joints, the construction of the boiler along the way. Some are only a hydro test. Some hydro test to 1.5 times, some hydro test to 2 times working pressure, and so on. In my case, I've been in contact with the club along the way here, where I hope to run this locomotive someday. They've been inspecting the joints as I've built this thing, and they're also, of course, going to be hydro testing it at the end. So, and then they'll certify my boiler for 4 years, and then every 4 years it'll get recertified if I want to continue to run it at their track. So that's the process. I hope to bring you along when I eventually do get this boiler certified, but they've, as I said, been inspecting it, and they're confident that it's going to pass their certification hydro test. I sure hope it will. We'll find out as soon as I'm able to get over there and take it to them. I had some folks ask about things like scribe lines and punch marks on boilers. A lot of folks had the notion that this would create a weak spot in the material and thus would make the boiler unsafe. This is an area where a little bit of knowledge is dangerous. I think we all know that idea that, you know, sharp edges and surface damage can weaken a pressure vessel, but this is one of those things where scale matters, right? Model boilers are overbuilt to a bananas degree. I did the math on all this if you're interested in my vertical fire tube boiler build series, but the gist of it is that model boilers are typically overbuilt with a safety margin somewhere in the 1000% range. So a scribe line or a punch mark in the material is nowhere close to making the boiler unsafe. A way to think about it is, if these boilers were engineered so close to the edge of physics that a scribe line on the material would make that boiler dangerous, you couldn't run them. They wouldn't be safe. You know, these boilers have to be built to be moved around in trucks and kicked by teenagers at public tracks and these sorts of things. So they're not so finely engineered like a rocket booster or fuel tank or something, where they're right at the limits of physics and engineering to where the tiniest imperfection would cause a failure. Again, otherwise they wouldn't be safe to run at all for us plebes. So don't worry about the scribe lines. Kozo himself scribes his materials when he's building a boiler. You can see his scribe lines in the photos in the book. So if it's good enough for him, it's good enough for me. When it comes to finding leaks, a lot of folks ask about using dye or using some sort of soap and air pressure system. The latter is commonly used in fuel tanks, for example. So if you've built a fuel tank, you've seen that process. Those are both great methods for what they're used for. They don't really apply to steam boilers, though, because they don't actually help solve the right problem. So using dye, for example, helps you see when there's water coming out of a joint, but seeing that a joint is leaking is not actually the problem that you need to solve. What's tricky is finding exactly where on the joint that pinhole is, and the dye doesn't actually help you with that. What happens is the whole area is wet, and you have to keep drying off the area to find where the drip is starting. And the dye doesn't help with that, because the whole area would just be covered in green or purple water instead of regular water. And the other risk there is, I don't know how that dye interacts with flux, pickling acid, and silver solder. So I don't know what's in those dyes, so I wouldn't trust that dye seeping through that joint isn't going to contaminate that joint and keep me from fixing it. So that's why I don't think that there's a lot of value in the dye. As to the air pressure and soapy water or immersing the boiler after air pressurizing, some folks do that as a preliminary step in boiler building. If you're going to do it, only do it at very, very low air pressures, like 1 or 2 psi max. 5 psi doesn't sound like a lot because it's a small number. Thanks, Sprocket, for bumping the camera. It doesn't sound like a big number, but 5 psi of compressed air in a volume this big is a lot of energy. That's actually a dangerous situation. If you had a joint fail, that could be an explosion. And this is why we hydro test, because hydro testing is safe no matter the pressure. The boiler cannot explode with pressurized liquid. And the other reason that I think the air pressure testing doesn't buy you a lot is that it's good for finding water leaks, but something that leaks, something that does not leak at 2 psi probably will still leak at 200 psi, and it has to pass 200 anyway, so you might as well just start with the hydro testing because you have to test at those high pressures anyway. Air pressure testing with soapy water is great for making things watertight. You know, people that build fuel tanks, for example, use it for water tightness, and it's great for that. But I don't think there's a lot of advantages to doing it on a boiler, and it can be dangerous. So personally, I just stick to the hydro testing. Now, what's the deal with reheating old joints? A lot of people want to know more about this, and it's a great series of questions because it's kind of the dark art of boiler making. This is really where the rubber meets the road, where the skill is, where the experience comes in. How is it that sometimes you can heat up an old joint with the torch and it reflows and sometimes it doesn't? You can see that in my boiler build series. You'll see that torch right on lots of joints. And sometimes those joints are fine and sometimes they fail. There is a hysteresis to silver solder. Once you've flowed it once, it takes more heat to get it to flow again. It's not like electrical solder that reflows at the same temperature every time. So that helps a lot. The other thing that helps is because I'm using plain propane, which is really only a little bit hotter than is needed to flow the silver solder. What that means is that even though the torch flame is big, only the joint kind of right in the center of the torch is really getting hot enough to flow solder. So the joints that are nearby don't quite get hot enough to flow. And so that really helps you a lot. Heat conducts into those areas, but the conduction is really not quite enough to get those surrounding areas hot enough. And again, the incredible heat sinking ability of copper sinks away most of the heat and actually protects those old joints. Now, when a joint tends to fail, I think, and again, I'm not an expert at this, but what I believe is happening is if an old joint is really close to the one you're working on and is again directly in that torch flame and at the same distance and angle to the torch flame as the joint you're working on, because those variables both matter a lot too. The joint that's directly under the torch and the most directly hit by the flame is the joint that gets the hottest. It also matters what's around the joint. So a lot of times when you see me following Kozo's suggested order of operations for this boiler because he's worked out what's the safest way to do all these joints, a lot of times an old joint is safe because it's protected by the other things it's connected to. So a lot of times, for example, when you see me doing the tube sheet or the backhead joints, there's stay bolts there that don't reflow, even though they're right in the torch. And it's because the other end of that stay bolt is connected to a big copper structure that's not under the torch. And so it's sinking that heat away and protecting that upper stay bolt joint. So these are the details that really separate a novice from an expert in silver soldering boilers, and why I'm so glad to have the benefit of Kozo's experience guiding me through this process, because otherwise I wouldn't know what order to solder all this stuff in, and I would be ruining old joints right and left. A sort of related question that people ask a lot is, why do you use such a big torch instead of a small torch or a hotter torch like acetylene or oxypropane? Again, I've answered this question many, many times, but I'll try one more time. You have to use a big torch because of the mass of copper. Copper is an incredible heat sink, and if you've never experienced silver soldering or soldering of any type on a 12-pound chunk of copper, then you really haven't seen the incredible heat sinking power of that metal. You have to use a big torch because you have to heat up the entire area around the joint. The problem with things like acetylene and oxypropane is that the torch tip, the flame that comes out of the torch, is very, very small. And that heat is so focused that you will never get the overall joint hot enough to flow the solder before you actually destroy the fittings and the material in the area. So if you just take a cold boiler and point an oxyacetylene torch on it, you will punch a hole in that brass or in that bronze fitting that you're trying to solder before the joint gets hot enough to flow the solder. I know it sounds crazy, but that is really what happens. So the whole point of using the large propane torch is that you're heating up the entire area and you're keeping that mass of copper from bleeding the heat away from the joint and preventing the silver solder from flowing. So using a smaller torch does not prevent you from damaging other joints or putting heat where you don't want it, because you have to heat the entire area to make a good joint. You have to. So that's why you have to use a large torch and then use other techniques to keep other joints from being damaged by that large flame. Another common question was about the brass fixturing screws. As I've said in my boiler build videos, and as many of you know, brass is a no-no on boilers because, of course, live steam leaches the zinc out of brass in a process called dezinkification, weirdly enough, and causes the brass to get brittle, and it can fail over time. So you might reasonably ask, why are those brass screws okay? Well, if you look really carefully at Kozo's design, virtually none of those brass screws are actually exposed to the steam. They're all either completely encased in copper or they're below the water line. So they're underwater in the boiler, but they're not ever exposed to live steam. There's one or two maybe on the top of the crown sheet that might be exposed to live steam, but otherwise none of them are. So that's point number one. Point number two is that, like most things in machining and mechanics and, well, life, none of these rules are absolute, right? It's certainly best practice to avoid brass in boilers, and you certainly don't want to make, really critical components out of brass, but also it's not that big a deal for a boiler like this where it's going to get fired a dozen times, maybe it's in its entire life, and it's a very small piece of brass that's hardly exposed to live steam very much. So while dezinkification is a real problem, and you certainly wouldn't want to use it in the steam catapult launch system of a Nimitz-class aircraft carrier, a little bit of it here and there in a model boiler is fine. Again, referring to the 1884 model engineering articles, those guys used to build entire boilers out of brass, which is not something we would recommend nowadays, but the point is, it's not such a big deal that any amount of brass is the end of the world. So let's just all take a breath. The next question I'll answer as a group, which is just various design concerns about the boiler. A lot of folks said, this or that shouldn't have been done that way. Oh, that foundation ring should be all one piece. Or, oh, that throat plate joint is a bad design, yada, yada. I think, again, the thing to keep in mind here, in the spirit of intellectual humility, is that Kozo knows what he's doing. He has designed and built more locomotives than you and me put together. And the A3 Pennsylvania switcher in particular is a very proven design. There are hundreds of these locomotives that have been built and run successfully for many, many years. So while I'm sure there's many improvements that could be made to the boiler, it's a very adequate design. It's perfectly fine, and there's really no major issues with the design. So if you want to think of ways to improve the boiler, that's great, but again, don't look at what you see me doing and assuming that I'm designing something crappy, because again, I'm building it right to Kozo's drawings, and it's a very, very proven design. Probably the most proven live steam locomotive design out there, except maybe some of the British ones like the little titches and stuff that people have built probably thousands of. One fellow asked, how can you possibly ride on this locomotive? It's not that big, right? And when I started this series, I talked about how I wanted to build one of those locomotives that can pull you around in your yard. And of course, a 3.5-inch gauge locomotive can do that quite easily, but you don't ride on it. You ride on a riding car that sits behind the locomotive. And generally you run a locomotive like this at a club track, which you join and help maintain the track and so on, the facilities. And club tracks generally have what are called a high line, which is a 3.5-inch gauge, and other gauges as well, but it's primarily for the benefit of the 3.5 gauge folks. It's a line that's elevated above the ground so that you can straddle the track, and your little locomotive can pull you around at a comfortable ride height, essentially. So you can interact with the controls in a comfortable way. You can run them on the ground as well. There are photos of Kozo doing that in his book, for example, but that generally requires laying prone on a long flat car behind the locomotive, which doesn't look especially comfortable to me. So I will definitely be preferring to run this on a high line at a local club. Some folks have asked, that boiler isn't very big. How can this thing possibly pull one or more adults around on a track, which was, again, one of my goals. And again, 3.5-inch gauge locomotives have been doing this for many, many years, and they absolutely can do that. And the reason that they can do that is partly because you can get quite a bit of power out of coal in a steam engine, but also this is the whole point about trains. This is why trains are great, right? It's their efficiency. It's steel wheels on steel rails. It's low rolling resistance. That's the whole point of trains. And that benefit scales down, which is what's so cool about them. So your car, for example, wastes a lot of gasoline deforming your tires as you roll around on uneven ground. Every time that tire rolls, the bottom of it gets flat and then unflat and then flat and then unflat as that tire rolls. That deformation of the tire burns a lot of energy, and trains don't have to do that. The very same effect is true at this model scale. The train, once you get it rolling, it might have some wheel slip to get a heavy load rolling, just like real trains do. But once they're rolling, it takes very little energy to keep it rolling. And so that means you can pull quite a heavy load with relatively less power. So that's why this little locomotive can pretty comfortably pull around, certainly one adult and reasonably 2 or 3 as well. They're really limited only by traction. To that end, you want your locomotive to be as heavy as possible because that increases tractive effort. We don't really rate locomotives in terms of horsepower, although those numbers are also available. It's really more about tractive effort. How much can that locomotive pull? And the tractive effort of a Pennsylvania A3 switcher is more than enough to pull one adult. And if track conditions are right and it's well made, it'll easily pull 2 or 3 as well. Another question I'll answer in sort of a general way. Boiler making has a way of drawing in the jewelry makers because, of course, silver soldering and copper and so on, a lot of overlap there in interest. So a lot of the criticisms people give of things that they see me doing in this build are down to experiences they've had jewelry making. I will just say that that's a very different discipline with different requirements, different challenges than boiler making is. Again, largely due to the masses that we're talking about. Again, 12 pounds of copper does things that an earring made of copper does not. So that's why we use different tools, different techniques, and different materials. A lot of folks ask about pickling. What is pickling? And what am I using for that? I have tried to explain that in many videos along the way here, but I'll explain here again. Pickling is simply soaking the boiler in acid for between 5 minutes and an hour or so, depending on what kind of acid you use. And it's just a chemical cleaning of the boiler. It prepares the metal for silver solder, and then after silver soldering, it cleans off all of the soot and the torch debris and so on, and makes the joint clean again so that you can inspect it for the next step. The pickling acid that I use is Sparex number 2. It's basically a kind of safer version of sulfuric acid. I forget what the actual chemical is, but it's often used in swimming pools as well. Although be careful because pH reducer in swimming pools is also just muriatic acid. So some swimming pool pH reducers are the same chemical that's in Sparex. But in any case, it's a little bit expensive, but I mean, that tub of it is like a lifetime supply. So it really goes a long way. I like Sparex a lot because it pickles the boiler in 5 minutes. A lot of people use citric acid as well, which is certainly an option, but citric acid takes more like a couple of hours. And when you're doing a lot of joints or when you're leak fixing and so on, having to wait a couple of hours for a good pickle is really slows you down. Even that 5 minutes sometimes feels like a long time when I'm trying to get a lot done. Some folks asked about preheating the boiler before silver soldering in an oven, for example. That's actually something I've tried. I gave that a shot in my very first boiler that I ever built. What I learned is that it doesn't really help very much. The hottest that a residential oven can get is 500 degrees Fahrenheit, and that's frankly getting a little hard on the oven. That's like approaching the self-clean mode on them. And it takes about an hour for whatever you put in that oven to reach that temperature. So you're talking about an hour of oven time. It's a lot of electricity, a lot of time, and it's only getting you less than a third of the way to silver soldering temperature. So it's really not helping that much. If you had a big heat treat oven or something that can get up to 1500 degrees, then that might be useful, but a big heat treat oven like that is an expensive toy. Meanwhile, the torch does it in 3 minutes. 3 minutes of the big torch and the whole boiler is at 1500 degrees. So the oven is a nice idea, but it just really doesn't help very much for what it costs and for how much time it takes. Well, I threw a lot of information at you there. Hopefully your questions got answered in there. Feel free to drop me an email or send me a note on Patreon. If you have more questions, I can do my best to answer. Again, I don't tend to answer questions in comments on the YouTube videos, but I do have an FAQ that I'll link below. And if people are interested, I might include some of this boiler information in the FAQ as well. Well, thank you very much for watching, and thanks to my patrons especially for making all of this content possible, and I will see you next time.